Welcome to the Network Plus Prepcast, your dedicated audio companion for mastering every objective on the CompTIA Network Plus certification exam. This series is produced by baremetalcyber.com. Classless addressing and variable length subnet masking represent a major evolution in IP addressing, replacing the rigid limitations of classful systems. In this episode, titled Classless Addressing and VLSM, we explore how these concepts allow for more flexible subnetting, better use of available IP address space, and improved network design. By moving away from class-based restrictions, classless addressing lets administrators assign addresses based on specific needs, making it a vital tool in today's networks. This topic is foundational for understanding modern subnetting methods. Within the context of the Network Plus certification, classless addressing and VLSM are core components of the subnetting and routing objectives. Exam questions often involve scenarios where you must apply these concepts to determine subnet sizes, allocate ranges, or troubleshoot conflicts. Because of their broad application in real-world networks and critical presence on the exam, a strong grasp of classless addressing and VLSM is essential for test success. You will need to perform calculations and make logical decisions about subnet allocation, especially in more advanced question formats. Classless addressing is a method that abandons the traditional reliance on address classes. Instead of using fixed boundaries like class A, B, or C, it uses CIDR notation to specify subnet masks. This notation allows any number of bits to define the network portion, giving administrators flexibility to create networks of nearly any size. Classless addressing enables networks to be customized according to actual requirements rather than being constrained by predefined address ranges, which improves efficiency and adaptability in both small and large-scale network environments. The benefits of classless addressing are numerous and directly align with modern network design goals. First, it allows for more efficient use of IP address space by enabling subnet sizes that match actual host needs. Second, it improves route aggregation by allowing multiple smaller networks to be summarized under a single routing entry. This reduces routing table size and improves performance. Finally, it supports hierarchical design, where address allocation can be structured in tiers, reflecting physical or logical network divisions, which simplifies management and troubleshooting. CIDR, or classless interdomain routing, is the specific technique that implements classless addressing. It replaces class-based notation by using the slash format to indicate the number of bits in the network portion of an address. For example, 192.168.1.0/26 indicates that the first 26 bits identify the network, leaving the rest for host. This flexibility means that network design is no longer limited to blocks of 256, 65,000, or 16 million addresses. CIDR is commonly used in both local subnetting and global routing tables. Variable Length Subnet Masking, or VLSM, takes classless addressing a step further by allowing different subnet masks to be used within the same address space. This enables administrators to divide a single IP block into subnets of varying sizes based on individual needs. VLSM is especially useful in complex networks with diverse requirements, where one area might need thousands of addresses and another only a few. The precision of VLSM supports efficient address utilization and is a common topic on the certification exam. VLSM is most helpful when designing networks that include locations or functions of varying sizes. For instance, a central office might require a large number of host addresses, while a small branch office might need only a few. Using VLSM, the administrator can assign subnet sizes that fit each site's needs without wasting addresses. This approach is also useful in designing networks with core, distribution, and access layers, where each layer has different capacity requirements. VLSM allows for granular allocation and maximum efficiency. When subnetting using VLSM, the administrator begins with a large IP block and then divides it into smaller subnets of different sizes. The best practice is to allocate the largest required subnets first to ensure they have enough space. Each new subnet is carved out of the remaining address pool, and careful tracking is essential to avoid overlaps. This process often involves calculating binary address ranges and mapping out the address space visually or with software tools. The goal is to ensure each subnet is properly sized and distinct. Routing protocols must support VLSM to take full advantage of its capabilities. Classless routing protocols like RIP version 2, OSPF, and EIGRP can advertise routes along with their subnet masks, which is necessary for VLSM to function correctly. When networks of different sizes are used, each must be specifically identified in the routing table. In some cases, these protocols can also summarize VLSM subnets into larger blocks, further optimizing routing. However, this only works when address ranges are contiguous and properly aligned. Fixed length subnetting uses the same subnet mask across all subnets, regardless of need. This results in simplicity but often wastes addresses, especially when some subnets don't require the full range. VLSM, by contrast, assigns subnet masks based on actual requirements. While VLSM provides much more flexibility, it also introduces more complexity. Proper planning, calculations, and documentation become critical, but the benefits include better use of address space and greater scalability. The exam often includes comparison scenarios between these two approaches. For best results when designing VLSM networks, start with a clearly defined, large address block. From there, determine the sizes of all required subnets and arrange them from largest to smallest. This order ensures that larger subnets are placed first, avoiding the risk of running out of space. Creating a subnet map or chart is highly recommended, as it provides a visual representation of address allocation and helps prevent overlap. Good planning is essential to managing the increased complexity that comes with VLSM. For more cyber content and books, please check out cyberauthor.me. Also, there are other podcasts on cybersecurity and more at baremetalcyber.com. Several tools are available to help with planning and implementing VLSM-based subnetting. Subnet calculators can quickly determine address ranges, subnet masks, and host counts for a given prefix length. In more technical environments, converting between binary and decimal formats manually helps reinforce understanding and aids in troubleshooting. Some professionals also rely on printed subnet tables or spreadsheets to map out address plans. These tools are invaluable for preventing mistakes and ensuring accurate subnet division, especially when working with variable length masks. In modern routing table entries that support VLSM, each route includes not only the network address, but also the specific subnet mask. This precision allows for more efficient routing and prevents unnecessary consumption of IP space. Unlike classful routing, which assumes a fixed subnet mask based on class, classless entries provide exact information. As a result, VLSM routes enable fine-grained control and improve address conservation, especially in large or complex networks where each block must be used efficiently. One of the major risks with VLSM is the potential for overlap or conflict between subnets. If two subnets accidentally share the same address space, routing protocols may not know which path to use, causing packet loss or misdirection. This is particularly dangerous when networks grow without a clear plan or when address assignments are done manually. Accurate documentation, well-maintained subnet maps, and proper hierarchy and address planning are essential to avoid these issues. The exam may include questions that ask you to identify or correct such overlaps. There are many real-world examples of VLSM applications. For instance, small subnets with only 2 usable host addresses are ideal for point-to-point links between routers. Meanwhile, larger subnets can be used for VLANs, or segments that support many user devices. VLSM makes it possible to assign just enough space to each part of the network without wasting address blocks. In the exam, you may be given a scenario requiring you to match subnet sizes to different types of network segments based on host counts and efficiency. VLSM is especially valuable in hierarchical network design. In this model, the core of the network receives the largest address block because it typically handles the most traffic and connections. As you move outward to distribution and access layers, smaller subnets are assigned to reflect their limited scope. This structure mirrors the physical layout of many enterprise networks, and allows for logical address assignment. Hierarchical designs using VLSM are more scalable and easier to troubleshoot, which aligns with best practices and exam expectations. Only classless aware routing protocols can support VLSM. RIP version 2, OSPF, and EIGRP are examples of protocols that include subnet mask information in their updates. These protocols recognize and preserve the differences between subnets of varying sizes. In contrast, RIP version 1 does not include the subnet mask and assumes default class-based boundaries, making it incompatible with VLSM. On the certification exam, you may be asked to identify which protocols support VLSM or to select the right protocol for a classless environment. Exam questions on VLSM often test your ability to calculate subnet sizes and assign address ranges without conflict. You might be given a large IP block and a list of departments with different host requirements, then asked to allocate the correct subnets. Questions may also involve identifying errors in subnetting plans or determining whether overlaps exist. To succeed, you must understand how to calculate subnet masks, determine usable ranges, and document address plans accurately. VLSM is a high-priority topic that integrates math and logical reasoning. There are several common mistakes to avoid when working with VLSM. One is skipping the planning phase, which can result in misaligned subnets or inefficient use of address space. Another is assigning overlapping address ranges, which can cause routing errors or broadcast issues. Lastly, failing to account for future growth can lead to rework and disruptions down the line. By avoiding these pitfalls, network administrators can ensure their VLSM implementations are both effective and scalable. The exam may test you on identifying and avoiding these issues. To summarize, classless addressing and variable length subnet masking provide the tools needed for modern, efficient use of IP address space. These methods replace the rigid boundaries of classful systems and enable networks to be designed according to actual need. Classless addressing uses CIDR notation to define custom subnet masks, while VLSM allows for multiple mask lengths within a single network. Mastering these concepts is essential for passing the Network Plus exam and for working in today's dynamic networking environments. Thank you for listening to this episode of the Network Plus Prepcast, your trusted audio guide to the CompTIA Network Plus certification. This episode was produced by baremetalcyber.com. For more cybersecurity podcasts, books, and resources, visit baremetalcyber.com. Thanks for joining us for this episode of the Bare Metal Cybersecurity Plus podcast. For more episodes, tools, and study support, visit us at baremetalcyber.com. And before you take the test, make sure to check out the practice questions in the book Achieve CompTIA Security Plus SY0-701 Exam Success by Dr. Jason Edwards. They cover every domain and are a powerful way to lock in your knowledge.